factoring polynomials over the real numbers and over the complex numbers. So up until this point in your math career, you probably have only seen one kind of factoring. And you might remember that when you see just a standard form polynomial, such as this one, you'd see a polynomial written as a sum of terms that are different powers of x. So in fancy notation, that would be a sub n x to the n plus a sub n minus 1 x to the n minus 1. And you'll notice that the indices here match each other because we're trying to make sure to match our coefficient with our power. And it's just a notation thing. I'm just putting it here so that you can get a little bit more familiar with seeing it, as you're going to see this kind of notation a lot in the future. So that's a standard form polynomial, and we're talking about factoring. So what is the factored form? The factored form is, instead of writing the polynomial as a sum of terms, you would write it as a product of terms. So you might have some sort of number that's a constant, leading coefficient, and then you'd have a product of factors. And again, you see that the indices on the powers match the indices on the zeros. So in this particular factored form, written very formally, your zeros would be x sub 0, x sub 1, x sub 2. And as we learned earlier, that zeros go with factors. So the zeros would be matching with the x minus x sub 0 factors. Okay, so the main thing to notice is that the factored form is a product of terms and the standard form is a sum of terms. Something that you probably remember from algebra is that not all polynomials will factor into a product of real number factors. So you might remember doing something with a quadratic formula, maybe getting an imaginary number, and then saying something along the lines of, oh, there's no solution, this one doesn't factor because I'm getting a complex number. So that's where we're really expanding on our concept of factoring. If we allow complex numbers to go in the positions of x sub 0, x sub 1, x sub 2, it turns out that we can completely factor every polynomial, which is really, really awesome. So that's what we're going to be working on, is we're going to be working on distinguishing between factoring over R and factoring over C, as well as just reviewing and kind of enhancing our techniques for factorization. So let's get started on a really basic example with quadratics and just review a little bit and establish really clearly the difference between factoring over R and factoring over C. Okay, so let's start with the basic factoring over R. You might remember that the first thing that you try and do when you're factoring is see if you have any common factors to your terms and pull it out. And I noticed that we have a common factor of 2 to all of our terms. So I'm going to factor the 2 out, leaving me with 2 times x squared plus x minus 1. Okay, now I have a quadratic, and I might think to myself, maybe I can use factor by grouping. Are there maybe 2 things that will add to the middle coefficient and multiply to the last coefficient? So I'd be looking at numbers that add to 1 and multiply to -1. And off of the top of my head, I don't see that happening. So we'll jump into the quadratic formula. Okay, so the quadratic formula is x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. And we'll simplify. And that ends up being 1 plus 4, which is 5. Perfect. Okay, so these are going to be our 2 zeros. And remember that we've learned that there's a connection between zeros and factors, and that is that x minus a 0 is your matching factor. So our 2 factors would be 2 as the leading coefficient times x minus -1 plus root 5 over 2 times x minus -1 minus root 5 over 2. And I'm adding in these extra parentheses just because I really want to be careful, not make any mistakes with my negatives. Okay, so notice that this polynomial factored completely over R. So I've already broken it down as much as I can. It matches this format of having possibly a leading coefficient and then x minus a real number factor. So it's factored over both R and C. Okay, so we just learned the lesson that when something factors completely over R, that is the factorization over C, and that's just because the real numbers are just a subset of the complex numbers. Okay, so once again, when something factors over R, that's also the factorization over C. Okay, so let's take a look at this quadratic. Let's see if maybe the factorization is a little bit different. So again, I'm going to notice right away I see a common factor of 3 that I can pull out, and let's just go ahead and pull out the whole negative 3. So that leaves me with x squared minus 2 and okay, so this one actually it looks like it's probably going to factor over R again. So we get negative 3 times, and look at this. This is x squared minus a number. This is called a difference of squares. So the pattern for this is that we can break it up into x minus root 2 times x plus root 2. Okay, so the pattern for any quadratic without that middle term is just that you can do x minus the root of the constant, x plus the root of the constant. That's a special form that we'll add to our toolbox. I wanted to do one that had a different factorization over R and C, so I'm going to add in another example. Let's do part C here, and let's do something like x squared plus 4 over R and C. Okay, so when I try and do this with x squared plus 4, what I notice is that it looks like when I do my quadratic formula, I'm going to get all imaginary zeros. So I get plus or minus root 16 negative all over 2. And I can break that up by pulling out the root negative 1. And I'm left with the root 16. So I get plus or minus 4i over 2. So plus or minus 2i. Okay, so I notice that my zeros are complex. So for this particular quadratic, our factorization over R will be x minus, and this is actually the factorization over C, would be x minus 2i times x plus 2i. This is my factorization over the complexes. And then over R, the factorization is just the original quadratic, as we couldn't break it down. Okay, so sorry for the crowding there, but our factorization over C is definitely different than the factorization R for this example. Okay, so I think this one highlights the idea of what we're going on for here. We're going to get a little bit more broken down over C than over R. Okay, so let's take a look at just our general toolbox for factoring. Okay, these are the strategies that we're going to have in our toolbox to factor over both R and C. Some of them we've seen before, and some of them you may have seen, maybe forgotten. Some of them maybe you've never seen at all. That's perfectly okay. So the first thing that we always try when we're going to factor is we're definitely going to factor out the GCF. Okay, the greatest common factor, if there is one. So if you notice that all of your terms in your polynomial have a common factor, whether it's some power of x or just a number, you can factor that out to start with, and it's definitely helpful. Okay, the next thing you want to look for is maybe you have some sort of special form. So if you have a difference of squares, which we saw already, that's one common kind of one. So a squared minus b squared. This one would be a difference of squares. And it factors as a minus b times a plus b. Okay, next would be the difference of cubes. Okay, so a cubed minus b cubed would factor as, now this is going to be our little mnemonic for helping us remember both the difference and sum of cubes. It's the mnemonic SOAP. So the way it goes is you're always going to have a linear factor and you're always going to have a quadratic factor. So the linear factor is going to have a and b, but the sign for the b is going to be the same, so S for same, the same sign as here, so same. So a minus b, and then you're going to have the opposite sign, so the opposite color. And then you're going to have always positive. So it doesn't matter what, always positive. Okay, so let's do the sum of cubes using that pattern. Okay, so AB, and then this should be a squared, minus AB plus b squared. Okay, so same, positive, opposite would be negative, always positive, b squared. Okay, that is called a sum of cubes. Okay, so those are the three special identities that I find myself using all the time. There's maybe... No, I really think of those as kind of like the three main special identities, and you guys can let me know sometime if you're thinking of any that you really like to use, but those are the three big ones that I can think of. Okay, so let's talk about the next strategy, which would be what happens if you have something that's like a quadratic. And I don't want to say like just quadratic, because it could be also quadratic type. Okay, so let me clarify what a quadratic type is. Quadratic type is something like, for example, x to the fourth plus 2x squared plus 1. Okay, so why would that one be a quadratic type? Is because we look at the powers, we still have the basic pattern of a quadratic. The leading power is 2 times the middle power. We can see that this really still feels like a quadratic. So it turns out that if it's quadratic type, you can factor it using the same kind of strategies you would factor a quadratic, using either the quadratic formula or something like factor by grouping or another by hand method to break it down, which is really cool. So we'll see an example where we do that a little bit later. Okay, so that will be the next thing we would look for. Okay, next, let's say we still need to factor something. Next, we'd probably try factor by grouping. So factor by grouping is really nice for when you have an even number of terms and you can see that in pairs, your terms have a common factor to each pair. So it should be the same common factor, and you'll see it in each like set of pairs. And this doesn't always work, definitely. There's definitely things with an even number of terms where you can't do this. So this one's definitely, let's do a little exclamation point. It's like, okay, it's not always possible, even for the polynomials with an even number of terms. It's just something to think about, basically. So for some of them, it's going to work, and for some of them, we're going to have to try something else. Okay, so let's go ahead and just make a note that that is also great for polynomials, for quadratics with integer roots. So let's say you have something that is a quadratic that has 3 terms. If it happens to have either integer or I think rational roots as well, this would work. Where it starts to get dicey is it's not going to work for you if you have irrational roots, basically. You won't be able to, it won't be as easy to do it, basically. So the next strategy, kind of our worst case, and this is going to be where it's very, very individual to your course experience. So you're going to want to consult with your class notes, your teacher, your experience to see what they have to say about if all these strategies have failed. So it's going to depend a little bit in the nature of your course, what the teacher's trying to emphasize, basically. So some courses and some institutions are very, very dead set on not allowing the usage of technology. So I'm going to pretend that everyone's going to be at some point expected to at least kind of be able to figure this out without having technology. Let's say you did have technology. What you could do at this stage is if all these strategies have failed, your calculator can do a pretty good job of graphing in a way that'll allow you to at least see where the roots are. And what you'd be hoping for is you'd be hoping that you would be able to get your calculator to give you exactly at least one of those roots. Okay, if your calculator is giving you these decimal approximations, that would mean that all of the zeros for your polynomial are likely irrational and that your calculator is numerically approximating them. So what you're hoping for is that your calculator is going to give you a nice, clean rational number, and then you'll be able to have your first factor to use synthetic division with to try and break your polynomial down further. And again, we'll see some examples where we're doing all this later. So for now, just kind of outlining the strategy. So your calculator can be helpful here, but let's say you weren't allowed to use one, or let's say you just found yourself needing to do this and you didn't have technology for some reason. There is a theorem that can be really, really helpful, and that's the rational roots theorem. So the rational roots theorem, I have it detailed in my course elsewhere, so I'm not going to go over the full details here. But basically the rational roots theorem says that if you have an integer leading coefficient and an integer constant, then you can make a list of possible rational roots for your polynomial. So the list of possible rational roots is plus or minus the factors of a constant over the factors of the leading term. And I should be a little bit careful. It's not really the leading term, it's the coefficient. So it's just the number part of it. Okay, and also note that these are possible. Not all are winners. Okay, so basically it's a list of things to guess. So that's the part that can be a little bit motivating as to why technology is so useful whenever we can get developments, is that if you have technology, the guessing part of it can be a lot quicker. So let's say you did have a calculator, and you can use your calculator to kind of visualize which of these zeros appear to be the winners. Then you can use that along with your synthetic division to get your factorization. So what's going to happen in calculus, which is really motivating our study, and it's unfortunate you guys haven't seen calculus yet to know, but basically there's going to be some things called integrating and some other situations where you'll want to have your polynomials factored. Now your calculator can do a great job at numerically approximating zeros, but the way that it works behind the scenes with the programming is that it's not computing exactly all real zeros. It's numerically approximating the irrational ones. So we really have to have lots of these by hand strategies to actually get our hands on the exact factorization. So like, for example, the simple parabola x squared minus 7. If you tell your calculator to find the zeros, it will give you the zeros in decimal form. It will not know that the zeros are plus or minus root 7 because of how your calculator works. Anything without a computer algebra system will not know how it's working. Okay, so at the end of all that, let's say we've got our hands on at least one rational root for the polynomial. That's excellent. What we're going to do from there is we can use synthetic division to, one, verify that we have a zero, but more importantly, factor. Okay, so what we're doing essentially is using the synthetic division to divide out the factor that goes with the zero that we found, and then get a polynomial that's now smaller that we can then continue to go back to our list. So we'd go back to the top and then just repeat. See if there's any of these strategies we can use on our new smaller polynomial. Okay, a lot of talking there, but those are our tools for factoring. So that's pretty much all the strategies that I use day to day when I factor things. Okay, there's some other ones that are briefly mentioned in some textbooks, but they're not things that we cover and stress in our particular course, so I'll leave those to you to investigate if you're interested. Okay, so before anyone goes panicking, I purposely tried to craft a polynomial that utilized every strategy that I use factoring. So I wanted to find one that had all of those strategies within it. I do not typically give you things like this on an exam. So if you're one of my students watching this, I wouldn't give this polynomial to you on a test by any means. What I would do is I would give you a polynomial that is a lot more reasonable under a time constraint, which is what you're going to be under. So this 6th degree polynomial with all these large number coefficients would not necessarily be something that I would test you on. Maybe it would be one of your harder homework problems, but don't be panicking about that. Okay, so I'm just trying to explain with something that has all the strategies here. Okay, so let's pretend we don't know how to factor this, which I bet hardly any of us do, right? Because it's pretty big. Okay, so let's start at the top of our list. The first thing we're going to do is look for that greatest common factor. So the first thing that I'm seeing is that it looks like 3, 3, 15, 3, 54, 36. It looks like all of these have 3 as a factor. So maybe even you could factor out a -3. So let's factor out a -3. Okay, and just make sure that the signs switch on all of these. So it'll be x to the 6th plus x to the 5th minus 5x to the 4th plus x cubed. 54 would be 3 and 18. And then 12. And then 72. Okay, now before we go on any further, we just want to be very careful and methodical and check. So switches to positive, switches to positive, switches to negative, switches to positive, switches to negative, switches to negative, switches to positive. Looks good. Okay, now let's jump in, and I'm looking at the number of terms. I'm trying to see if I see anything special. I definitely don't. I'm also looking at this and I don't see an even number of terms, so I'm not seeing anything that I can factor by grouping. I'm not seeing anything that looks quadratic in type. It definitely has way too many terms to be quadratic in type. So I'm looking at basically this is one where my only choice is the rational roots theorem. Okay, so we're going to do the rational roots theorem. And remember how we do this is we're going to build our list of possible zeros. So the factors of the last are the factors of 72, and the factors of first will just be 1. Okay, so let's do the factors of 72. They would be starting from the bottom, 1 and 72. And then next would be 2 and 36. Trying to leave space because once I meet up in the middle, I'll be done listing factors. Next will be 3 and 24. Next will be 4 and 18. Sorry for the pause there. 5 doesn't go into 72. Next we'd have 6. And 12. Then we'd have 7, does not go into 72. We'd have 8 and 9. Okay, and I've already hit 9. Okay, so our list has met up in the middle. I can go ahead and move these in. Okay, and remember our list of possibles would be plus or minus all of these. So all of these over 1. Okay, so some students draw the bar there. Remember you're matching systematically. So it'll be 1 over 1, 2 over 1, 3 over 1. And you just go systematically matching like that. So we end up getting plus or minus 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, 72. Okay. So if I were completely without technology at this point, what I would do is I would start low and I'd be hoping and praying, honestly, at this point. If I was allowed the uses of technology at this point, what I would do is I would probably honestly use the graphing calculator to kind of guide me in the right direction. So I'd look at it and I'd try and eyeball, do I see a 0 near any one of these? So that might help me make a very informed, quote, guess, right? But that's kind of cheating, right? So if I didn't have a calculator, I'd probably really, really just hope that 1 worked, and I'd start from there and work my way up. Let's go ahead and try -3 as a guess. Okay, and let's check with the synthetic division. So remember to do the synthetic division. You make sure that you get the coefficients for all powers of x. Okay, that includes the zeros. So if you're missing a term, you still need to put a 0 there. This one isn't missing anything because this one's a beast. Okay, so 1, 1, -5, 1, -18, -12, 72. Looks good. Okay, coming down, carry the 1 down for the first step. Then it proceeds to do multiply, carry, and add. So multiply, -3, carrying that over, Adding down, negative 2. Negative 3 and negative 2 is positive 6. Negative 5 plus 6 is positive 1. Negative 3 times 1 is negative 3. 1 plus negative 3 is negative 2. Negative 3 times negative 2 is 6. Negative 18 plus 6 is negative 12. Negative 3 and negative 12 is positive 36. 36 minus 12 is positive 24. And then negative 3 and 24 is negative 72. Yay! Okay, so you probably remember from the remainder theorem that remainder from the synthetic division means that having zero remainder means we found a factor. So let's write and recall that the factor we found is that x minus negative 3 is a factor, so it'll be x plus 3. And now I'm going to carry down my factorization. There was a leading term of negative 3. Carry that down. We've got x plus 3, and then we have x to the 5th. We divided out 1x, so x to the 6th becomes x to the 5th, negative 2x to the 4th, plus x cubed minus 2x squared minus 12x plus 24. Okay, now this part, I really, really like how this one worked out. I got really excited when I saw it earlier, not gonna lie. So take a look at this. We have an even number of terms, and I'm gonna highlight the pairs. First pair, I'll do pink, green, and let's do yellow. Okay, so we got our pairs here. Now I'm going to look and notice that it looks like between all those pairs, x minus 2 is a factor of each. So if I factor out an x to the 4th, I'm left with x minus 2. And for this factor, if I factor out, and okay, you can't cheat here. You have to actually be able to factor out something to leave you with the x minus 2. So I can factor out an x squared and do that. And for this one, if I factor out a negative 12, I have an x minus 2. Okay, so now I have a factor of x minus 2 that's common to all three of these, so I can pull it out to the front. So this is having a GCF. We just identified a greatest common factor to this sum that we can pull out. So when I pull it out, I'm left with x minus 2 times x to the 4th plus x squared minus 12. Where did those numbers come from? Right there. Okay, so now I'm going to keep carrying down my factoring just so that I don't forget anything. And I'm still not done because I have a 4th degree polynomial, which means I definitely can find a 0. I can definitely find at least, a complex 0 to that. So I have to at least see. I have to at least see if I have real number factors. Okay, so this one, check it out. I go down my list and I don't see a GCF. I don't see a special form, but I notice that I have that cool little pattern on the powers. 4 is 2 times 2, so this one's looking a lot like a quadratic. This is definitely a quadratic type, even if it's not actually a quadratic. But it means I can use my quadratic factoring strategies. So I'm going to practice doing factor by grouping. Okay, and this is one of the most underrated, but honestly the most awesome methods of factoring. Totally recommend, okay? If you're someone who doesn't do great with guess and check on these, factor by grouping saves the day. So what you do is you do the first coefficient times the last coefficient, so AC, and then you look at the middle. Okay, now remember you're looking for two numbers that multiply to the AC and add to the B, so I see 4 and 3, and which one should be negative? Looks like 3 should be negative. Okay, so what we're doing is we're unwrapping the distribution, aka the FOIL process. We're basically going reverse of FOIL. So I'm writing out I'm basically uncombining like terms. So x to the 4th plus 4x squared minus 3x squared minus 12. Okay, now notice I have not changed my original polynomial. Okay, and 4x squared and negative 3x squared still adds to 1x squared. So I didn't make anything up here. I just wrote it differently. And now check it out. I have pairs of terms again. Okay, and more importantly, my pairs have a common factor of x plus 4. So if I factor out an x squared from here and a negative 3 from here, sorry, it's an x squared plus 4 that's common. Then my factoring is x squared minus 3 times x squared plus 4. Okay, and we're almost done. copying my factoring down. This is where being systematic really pays off because it's super easy to drop factors on these really long ones like this. Okay, now looking at this, I have two quadratics possibly that could be factored. Hopefully you've seen enough of these at this point to feel like maybe you see a pattern and that last factor of x squared plus 4 doesn't have real zeros. But we'll see what happens and just kind of pretend we don't see that. Okay, so let's factor the x squared minus 3. This is a difference of squares. Okay, and I know how those factor. X minus the root of the second term, x plus the root of the second term. Okay, now we're going to try and factor that x squared plus 4, but we'll see what happens with it. Okay, so this is not any sort of special identity, but when I try and find the zeros, I could do my quadratic formula, or I could just do something as simple as setting it equal to 0 and solving. On the sum of squares, it's really easy to do that. Root of a negative, so it's going to be complex. Okay, so the zeros are plus or minus 2i. So that means that we've done as much as we can over r. This is my factorization over r. Okay. So that's part 1 of the answer. Okay, it also asked us to factor over c, so then we'll write out the last two factors. It would be x minus 2i and x minus negative 2i, so x plus 2i. And still we would have negative 3 times x plus 3 times x minus 2 times x minus root 3 times x plus root 3 times x minus 2i times x plus 2i. Okay, so that's our factorization over c. Okay, before we say goodbye for today, let's take a look at how we know we're done. So I know I'm done because all quadratics have been broken up. You shouldn't be left with any quadratics standing when you're factoring over c. The second thing I just want to point out is that this one would be very, very hard to factor just by looking at the graph. Okay, because if you think about it, what is it going to look like on a graphing calculator? First of all, x minus 2i times x plus 2i is not going to be captured on your picture. You won't be able to see those because those are complex zeros. So x squared plus 4, that factor wouldn't really be shown, wouldn't visually be looking like anything on the picture. Okay, and then your calculator would honestly even struggle with this x minus root 3 times x plus root 3, because your calculator would probably tell you that it's going to be something like 1.47 blah 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 and go about 6 decimal point places out, because calculators like the TI-84 are numerically approximating the zeros. They're not giving you exact. So for situations where you can round, it's totally okay to use technology, but if you're looking for something to be exact, you can't expect a calculator to be able to tell you that it's root 3 and negative root 3. So hopefully this one empowered you and made you feel like you can tackle anything, because we literally just looked at all the different strategies to factor these. And I'll see you guys next time.